Alright, so in the previous video we took a look at how we can represent straight lines in 2D Cartesian space using the equation y is equal to mx plus c. But there are a couple of special cases that I wanted to point out. These are when we have perfectly vertical lines and perfectly horizontal lines. When we have horizontal lines, we're going to see that this equation sort of simplifies down and changes slightly. When we have vertical lines, we're going to see that the equation here does not apply, and instead we're going to have a different form of equation. And you may wonder why we're pointing this out. Well, it's going to become important in the next video where we try and derive some formula for determining the equation of a line given 2 points. We just need to be aware of these special cases. So in the first case I said we have horizontal lines. So if I was to draw a perfectly horizontal line, for example something like this, well, this line, we notice, has a gradient m equal to 0, because no matter how far we travel in x, we never move in y. We don't move up in y or down in y. And because of that, m is equal to 0. So if we put m equal to 0 into our equation, we're going to get y is equal to 0x plus c. Therefore, y is equal to c. Thus, it doesn't matter which values of x we put into our equation, no matter where we sample this line, we always get the same value for y, and that value is where we cut the y-axis. In this case, I guess it's about 3.4, so we'd say y is equal to 3.4. So horizontal lines are simply written as y is equal to c, though that does relate to our straight line equation. It's just that the mx term of the equation has become 0 all the time due to the gradient being 0. So another example, if we had a straight line, say down here at -6, y is equal to -6 would be the equation that represents that line. The more complicated case, if you will, is when we have a perfectly vertical line. So when we have a perfectly vertical line, we're going to have something that's similar to when we have a perfectly horizontal line. So a perfectly horizontal line was y is equal to c. A perfectly vertical line is x is equal to some variable. I'm going to choose the variable a. So where c was our y-intercept, in this case a is going to be our x-intercept. And it's exactly the same form, but we're just saying no matter which y coordinates we sample, we're always going to return the same value for x. So in this case, x is equal to 3. If we had something, I don't know, down here, x is equal to minus 3.8. The reason that this is an interesting special case will become apparent in the next video, because we can't easily get to x equals a from the equation y equals mx plus c. And the reason for that is, think about the gradient here. We don't travel any distance in x, yet we travel infinitely in y. So our equation here kind of breaks down because our gradient, well really, that's equal to infinity. It's infinitely steep because we're a perfect vertical line. So instead of using y equals mx plus c to represent this particular form of straight line, these perfectly vertical lines, we use the equation x is equal to a. In the next video, when we start using the coordinates of 2 points to generate a line, we do need to be aware of the fact that if this is a perfect vertical line, we can't use this equation, we need to use this one. So I just wanted to point that out in this video so that in the next video, when we start generating straight line equations using the coordinates of 2 points, we know to look out for this particular special case where a line is perfectly vertical. So this is a very quick video, sort of a filler, if you will, between the previous video on the straight line equation and the next video coming up on generating the equation of the line based on 2 points. And that is going to conclude this video. Thanks a lot, everyone.